Hello, welcome back. In this video, we'll discuss how to bias a transistor, the circuit configurations and the working of a transistor. In a transistor, there are two PN junctions. If you look at the structure of a transistor, then say this is the collector, this is the base, the thinnest region, and this is the emitter. If you consider this to be a PNP transistor, then we have a junction here. The first junction, say there is one junction between the p-type semiconductor and n-type semiconductor. Similarly, there is another junction between n-type semiconductor and a p-type semiconductor in a PNP transistor. A similar thing also holds good for an NPN transistor. Since we have two PN junctions, there are four different ways to bias the transistor. The first possibility is both the junctions are forward biased. When both the junctions are forward biased, a large current flows across the junctions. A large current to flow across the junction. When large current flows across the junctions, we call the transistor as operating in the saturation region. Then the transistor is said to be operating in the saturation region. The second possibility is both the junctions are reverse biased. When both the junctions are reverse biased, a small current flows across the junctions. When a small current flows across the junctions, then this transistor is said to be operating in the cutoff region. The third possibility is emitter-base junction is reverse biased. Emitter-base junction is reverse biased and the collector-base junction is forward biased. Under such conditions, the transistor is said to be operating in an inverted mode. The last possibility is emitter-base junction is forward biased and the collector-base junction is reverse biased. Under such conditions, the transistor is said to be operating in the active region or normal mode. Now we shall look at the circuit configurations of the transistors. When we say circuit configurations, we generally refer to the active mode or the normal mode of operation. Means the emitter-base junction is forward biased and the collector-base junction is reverse biased. This type of biasing corresponds to the active region or the normal mode. We look at a PNP transistor that is operating in the active region, meaning the emitter base should be forward biased. Emitter is made up of a p-type material, base is made up of an n-type material. P-type material is the emitter that is connected to positive terminal of the battery, and base of the transistor should be connected to the negative terminal because the base is an n-type semiconductor. So this is forward biasing. Collector is a p-type material. It is connected to a potential difference VCB, which is greater than VBE. As a result, this will be a reverse biasing. And similarly, in the case of NPN transistor, the base is connected to the positive terminal of the battery, which is a p-type material, and emitter is grounded, which means we are forward biasing the emitter base junction. The collector base junction is reverse biased because the collector is made up of n-type material. We are connecting it to the positive terminal of the battery. We shall now look at the common base configuration. In these two configurations, there is one terminal that is common to both the input side and output side. We have the input side here and the output side here. The terminal that is common is the emitter. So this configuration is called as common emitter configuration. Now we shall look at the common base configuration of PNP and NPN. So the terminal that is common between input and output should be the base. This should be the common. Base is common between the input and the output. The condition is EB should be forward biased and CB should be reverse biased. Emitter is made up of a p-type material it is connected to a positive side of the battery, and base is an n-type material, it is grounded. So it is a forward bias, and the collector is made up of a p-type material, it is connected to the negative of the battery, which is reverse biased with respect to the ground, and again base is connected to the ground. So emitter base junction is forward biased and collector base junction is reverse biased. Same thing also holds good in this case. Emitter is made up of n-type material, it is connected to the negative terminal of the battery. Collector is also made up of an n-type material and it is connected to the positive terminal of the battery, and base is grounded. As a result, in this case also the emitter base junction is forward biased and collector base junction is reverse biased. We shall see a different type of configuration where the collector is made common for both input and the output. Here collector is grounded, collector is common. So this configuration is called as common collector configuration. In the case of a PNP transistor, emitter is here. Emitter is made up of p-type material. It is connected to the positive of the battery. Base is an n-type semiconductor connected to the negative of the battery. So this is a forward biasing condition. And collector is grounded. With respect to the ground, base is relatively at positive bias. So this is also a reverse biasing. So both forward bias for the emitter base junction and collector base junction reverse biasing are satisfied. So this is a normal mode of operation. Here also we shall see emitter is made up of n-type semiconductor, is connected to the negative of the battery. Base is a p-type material connected to the positive of the battery. So this is forward bias, and similarly the collector and base are reverse biased. So these are the three different configurations possible for the transistor, keeping one terminal as common between the input and the output. Now we shall see the working of an NPN transistor. The structure of an NPN transistor can be represented in this fashion. We have an n-type material, that is the emitter. P-type material is the base, and n-type material is the collector. Here also we will discuss the normal mode of operation for the transistor. In this, we assume that VBE is less than VCB. So emitter base junction is forward biased because n-type semiconductor side is connected to the negative of the battery, and base is a p-type material, it is connected to the positive of the battery, and again here n-type material is connected to the positives of the battery, which is a reverse biasing condition. In this, we assume that the potential difference or the biasing voltage applied between the base and emitter is less than the biasing across the collector base junction. We know that emitter is heavily doped in the transistor, and since it is forward biased, the majority charge carriers, the electrons, they move toward the base. When the electrons they move towards the base, it makes the emitter current. We represent with a IE. You know that the base is made up of a p-type material. A p-type material, which means the majority charge carriers in the base are the holes. And we know that base is lightly doped. What does it mean? It means concentration of the holes is small in the base, and we have the electrons entering the base material. So a fraction of the electrons entering into the base material, they recombine with the holes. After recombination, the remaining electrons, they constitute the base current, represented with an IB. This base current enters the collector's region, and in the collector region we have a reverse bias, meaning the collector region causes high attractive force for the electrons reaching the collector junction. So it causes high attractive force for the electrons reaching the collector base junction. Since a large amount of current is entering the collector region, heat also will be produced in the collector region. That is the reason why a large region for the collector is chosen, because it should also dissipate heat that is generated due to the flow of the charge carriers. So a majority of electrons emitted by the emitter flow into the collector and cause a large reverse current called the collector current, represented with an IC. We define a quantity called as transportation factor. It is represented with a beta, it is defined like this. The ratio of number of electrons arriving at the collector to the number of electrons emitted by the emitter. Typical value for beta will be close to 0.995, indicating that most of the electrons emitted by the emitter, they will be reaching the collector. Now we can write the emitter current IE as IB, that is the base current plus the collector current. Now we shall see the working of PNP transistor. Emitter base junction is forward biased. Base is made up of an N-type material. It is connected to the negative terminal of the battery. Emitter is made up of a P-type material. It is connected to the positive of the battery. Collector, which is made up of a P-type material, is connected to the negative terminal of the battery, and the base, which is made up of N-type material, is connected to the positive terminal of the battery. So this is a reverse biasing condition. The forward bias causes the holes in the P-type emitter to flow toward the base. This constitutes the emitter current, represented with IE. As the holes, they enter the base region, which is an N-type material where the electrons are the majority charge carriers. Some of the holes, they recombine with the electrons in the base. The remaining holes, approximately 95%, they cross over to the collector region, and they constitute the collector current. In this way, most of the emitter current enters the collector region. In this way, the entire emitter current flows into the collector region, and the current is mainly due to the holes. However, in a circuit, the current always will be due to the electrons. In this video, we have seen the biasing of a transistor, circuit configurations, and working of transistors. We have said there are two PN junctions possible in a transistor, and these two PN junctions can be biased in 4 different ways. The first possibility we have discussed is both the junctions are forward biased. When both the junctions are forward biased, a large current flows across the junctions. The operating condition is known as saturation region. The second possibility is both the junctions are reverse biased. When both the junctions are reverse biased, a small current flows across the junctions. This operating condition is called cutoff region. The third possibility is emitter base junction is reverse biased and collector base junction is forward biased. This mode of operation is called as inverted mode. The fourth possibility is emitter base junction is forward biased and collector base junction is reverse biased. This mode of operation is called as active region or normal mode of operation. We have seen the circuit configurations for the common emitter configuration of PNP and NPN transistor. In this circuit, the terminal that is common between the input and output is the emitter. So this becomes a common emitter configuration. We have seen the circuitry for PNP and NPN transistors. Similarly, for the common base, the base terminal is common for both input and the output. These are the circuit configurations for the PNP and NPN transistors in their common base configuration. In the common collector also, the collector terminal is common between both input and the output. We have seen the working of a PNP transistor. We have said VBE, that is the potential difference between the base and emitter, is smaller than the potential difference between the collector and base. And emitter, since it is made up of an N-type material, the majority charge carriers are electrons and they enter the P-type material, that is the base. Electrons that are entering into the P-type material, that is the base, they constitute the emitter current. Base, since it is made up of P-type material, the majority charge carriers are holes and the base is lightly doped, so small number of holes are present in the base material. The electrons that are entering the base material, they recombine with the holes. The remaining electrons, they constitute what is known as the base current. The collector is reverse biased, so it acts as high attractive force for the electrons reaching the collector base junction, and the collector current is represented with an IC. We have defined a quantity known as transportation factor, represented with a beta. It is defined as the ratio of number of electrons arriving at the collector to the number of electrons emitted by the emitter. The beta is close to 0.995. So we write the emitter current as base current plus the collector current. After that, we have discussed the working of a PNP transistor. Emitter base is forward biased, collector base junction is reverse biased. So the majority charge carriers in the p-type material are the holes, and these holes, they enter the base region, which is an n-type semiconductor. Since the base is made up of an n-type semiconductor, a fraction of the holes, they recombine with the electrons, and the remaining, they constitute what is known as the collector current. Within the transistor, the conduction is mainly due to the holes. However, when the transistor is connected in a circuit, the current will be mainly due to the electrons. Thank you.